constant. And r is constant, usually not 0. Does this look like a sequence? Right? Do you know the name of the sequence? This sequence has a name. Geometric sequence? The geometric sequence is a geometric sequence. We did that r to the k. When that r to the k converges, when the r doesn't converge, we did that, right? When it's 1, and it's a geometric sequence. Now you have a geometric sequence, of course, we can think about geometric series, which is the series associated with the geometric sequence. So let's write that down. What is a partial sum series? Always j going from 1 through k. I think this is the stage they often enter, I think, j equals 0 in here. Okay? This is standard. When you consider infinite geometric sequence, the k starts from 0. So the very first term here is a, next term is ar, next term is ar squared, things like that. Okay? So index usually starts from 0. So what's that part? aj. So this will be just notation definition for partial sum. So we go ahead and substitute a equals 0, the k, and a times rj. Is that right? R is fixed constant, a is fixed constant, right? So a is a constant multiple. If this is integral, what do? You can pull outside the integral, right? And we do the same. In that part a, there's no j. J is the variable for this sum. So a pulls out. Just really this one in here, r to the j. Okay? So this geometric sequence is algebraically very plausible. So we have a formula for this one. The answer is a times 1 minus r to the k plus 1 and 1 minus r. And you're supposed to memorize this. I'm going to explain where on earth it came from, but you need to memorize it. Here's how I want you to remember. Usually this one arises in more complicated form, so you don't have this cleanly divided shape. It looks a lot complicated usually in the problem. So suppose we're staring at this thing that's called, let's say, the bj. What you see in there is an expression in terms of j's. It looks complicated. And first to realize, is this coming from geometric sequence? Is this geometric sequence? To realize this complicated formula, this actual geometric sequence, is what you're going to calculate is that bj plus 1 divided by bj. You take that formula in j and compute this one. bj plus 1 divided by b. If this is a geometric sequence, what do you think this is going to pick up? If you look at this term with the j plus 1 divided by this term with the j. So let's pretend if this is geometric sequence, for which I don't know what a and r is, but if it is, what is this ratio it's calculating? So I'm just, without knowing what a and r is, I'm calculating this one. The things cancel out and leaving only r there, right? So if you don't know what a and r is, we only know from the problem that you have this bulk of expression appearing in the j. You calculate bj plus 1 divided by bj. And you do the simplification, and the number you were staring at has no j in it, right? If that's so, then it's a geometric sequence. It came from a geometric series. The r is that r. So we identify this one is a geometric series, and plus we got that common ratio r. Right? So this seems like the formula here involves r. We figured that out. And how about a? How do we figure out what a is here? Right? A is the very first term. This proves that it's a geometric sequence. A is that the bj, the b0 in there. Go and look at that formula and plug in the very first index. And that's the formula, right? The b0 is our a. So I got that part and got that part. Right? So here's a third part I want you to focus on. It's a really useful part. This k plus 1, you want to figure out the k plus 1. Don't think it is a top index plus 1. The better way to look at it here is that k plus 1 that goes to this numerator of this formula is the number of terms. You look at this entire sequence and you count the number of terms. How many terms are there? Starting from 0 and 1 and 2 all the way up to k. How many terms? K plus 1 terms, right? Including the index 0. So the number of terms appears over here. The common ratio you calculated by taking the ratio of adjacent terms appeared as this one, and a is multiplied to, as this is indicated here, a is multiplied to the whole thing. So that's how you read the formula. So we'll look at example and exercise what we just discussed in this later part in there. But hope this one is something you can remember. First term times this ratio, okay? This ratio. And there's this index, which is a number of terms. I'm changing this top. Good. So let's see. I'm going to write that down. I'll write that down in terms of j. J is starting from 2 and end up at n. And 3 times negative 0.75 raised to the jth power. That's what we're calculating. Good? So what do we calculate? 3 things for geometric series. What are those? A, common ratio, and number of terms, right? That goes in the formula. And in this process that you realize the common ratio depends on your index, then it's not geometric sequence. You can't use this anymore, right? This formula only applies to a special formula. So what is A here? Somebody like to volunteer for this one? What's A? What's that? 3. No, it's not 3. The very first term appearing when you plug in these j's into this formula. Squared, that's right. 3 is already there. Minus 0.75. The very first index we're trying is 2. So we've got to, this is our first term. Make sense? Right. That's why I was discussing that below. Don't look at the formula and judge from there. And just do what I do. It's a lot easier. Whenever they change this form like this, and then it's confusing. So, how do we get A? Plug in the first index. That's all you have to do. First index is j equals 2, right? You plug it in there. And that's your first term. How do you calculate the ratio R? Divide adjacent terms, right? So it's 3 times negative 0.75 j plus 1. If it is easy, if it is really easy to you, that is negative 0.75. I don't have to do this. That's fine. But whenever it's unclear, and check with this my calculator, this always work. So I'm doing that. 3 times negative 0.75 jth power. All right? Integrand applied in j plus 1 and j and divided. So 3 cancels. Exponential law says negative 0.75. Correct? Is there j in there? No j in there. This is something you have to check. No j. Students have tendency, because it looks nicer, so you just do that. If there's a j, they still plug it into the formula. If there's a j is in there, it's not geometric series, so you can't apply this whole method. Okay? So there's no j, so it's good. That's our r. How about number of terms? Who wants to go for that? N minus 1 is correct. If you start from 1 through n, then there will be n of them, right? So usually the formula is this. Upper limit minus a lower limit plus 1 is the formula. Upper limit you see is n, lower limit you see is 2, right? You subtract and add 1 more because it doesn't count the very first one. So that's why it's n minus 1. That's how you count the number of terms. So let's go and calculate this one. Let's remember how the formula goes again. What is the first factor of the formula? A, right? A is 3 times negative 0.75 raised to squared. That's the first term. How does the quotient part look like again? What's the denominator? 1 minus, right? negative 0.75, right? There's 1 minus r. And there's 1 minus r again, but there's a power. What is the power? Not n plus 1, right? Number of terms that you have calculated. That goes there. It's n minus 1. Make sense? So that's, no matter what n here is, if you use sage, that's exactly the same as this quantity right there. What? Okay, so we have calculated Sk is whatever this guy is. I'm going to kind of repeat that. But down there is 1.75. I could do that much. But the second term in the numerator, depending on the parity of n, it flip-flop to a positive and negative. So that's a closed formula. But often we're interested in the behavior of this one, right? Is that right? So where's the only part that involves k? Sorry, that I have to change that to k. K minus 1 up there. That's a partial sum. This is the only part that k appears. So if you know what happened to that guy, we have a conclusion on that one. So who knows what happened to that guy? Negative 0.75 raised to k minus 1, where k approaches infinity. This is again r to the k form, is it not? What do we know about r to the k? It's either go to 0, 1, plus minus 1, or goes to plus minus infinity. Something like that. Which one is it this time? 0, because absolute value of r is less than 1, right? R here is a 0.75. So that guy disappears. Very nice. So here's a 3 times negative 7.5 squared, right? Then this 1 is just 1 because this is approaching 0 this time, right? And denominator is 1.75. If you use 10 million terms of this one and use sage to add it up, that number is never exceed this number. It's always just around that point. There's a final destination of our walk that is instructed by this 3 times negative 0.75 to the j in your j-step move. And that's your destination. Final destination is right here. Make sense?